Hello, I am Young Kim from Hanyang University. I am a PhD student in Hanyang University and also a visiting scholar in Stanford University. Today I will talk about the effect of skull on pattern interference radiation force based on the focused transducer using Fresnel lens. These are the contents. Transcranial ultrasound stimulation, known as TUS, is one of the non-invasive neurostimulation methods, and it has high potential in neurological disease. Compared to other methods, it has high spatial resolution and high penetration depth. The conventional approach to TUS uses a single transducer focusing on the target, or the array is focused facing the same direction. In 2019, our group proposed the radiation force as the physical mechanism for ultrasound neurostimulation, and we suggested the pattern interference radiation force neurostimulator. Instead of using a single transducer, generating a standing wave with two focusing transducer creates a larger radiation force for neurostimulation. To stimulate the small area with PIRF, we needed to fabricate a large-size focused transducer, and we have decided to use the lens for focusing. The Fresnel lens was suitable than the spherical lens as it can be fabricated much thinner. To verify the Fresnel lens design, we have run the FEM simulation. The material used for the lens is Silgard 160, which is widely used for acoustic lenses. And we can see that it focuses well at the position we have designed as we expected. From these results, we have fabricated the large size transducer and the Fresnel lens separately and made the focused transducer for PIRF. We have measured the performance of the transducer using the membrane hydrophone, and it showed similar results from the simulation. The transducer has 1 MHz center frequency with the radius of 90 mm and the focal length of 63 mm. The input voltage was 25 volt peak to peak, and the 3 dB spot size was 7.4 mm and 1.5 mm with the focal gain of 24.2. To calculate the radiation force from the pressure field, we have used the equation for the acoustic streaming. It comes from the second-order process from the continuity and momentum equations for the fluid motions. With these equations, we have calculated the radiation force from the pressure field. For the PIRF experiment, we have used the lipstick hydrophone for the pressure measurement, and we have calculated the radiation force from the measured pressure field, which we can see on the right bottom image. After that, we have placed a tooth skull which has about 5 to 7 mm thickness, and we have measured the pressure field and calculated the radiation force also. From the result, we had about -11 dB acoustic loss from the skull. The thickness and the shape of the two skulls used in the experiment was very different, and because of that, the transmission rate of the right and the left side was different. So there wasn't a complete standing wave as we expected. So we have fabricated a large-scale acoustic Fresnel lens using PDMS for the focused transducer. And we also calculated the radiation force from the pressure field, including the effect of the skull. For future work, we are planning to do more experiments with better skulls to generate stronger radiation force by creating complete standing wave. And the lens with longer focal length are being fabricated for applications for full-size skull. Thank you so much.